Our next topic is Michelson. This is the schematic diagram of the Michelson interferometer. Here S represents a light source, and L represents a grounded glass plate from which a uniform plane beam of light is coming into. Then G1 is a beam splitter where a beam incident on G1 gets partially reflected and partially transmitted. Now M1 and M2 are good quality plane mirrors having high reflectivity. Here M2 is a fixed mirror and M1 is movable towards and away from G1. And in normal adjustment of the interferometer, M1 and M2 are perpendicular to each other and G1 is at 45 degree to the mirror. Now we are going to see how this interference happens in this interferometer. Waves emanating from the point P gets partially reflected and partially transmitted by the beam splitter G1, and the two resulting beams are made to interfere. Now look at the figure. The reflected wave, which is marked as 1, undergo reflection from M1, which is marked as 3, and this reflected wave gets transmitted through G1, which is represented as 5. Now the transmitted wave 2 gets reflected by M2, which is written as 4, and again it is reflected by G1, which is represented as 6. So in the figure, the beams represented by 5 and 6 will be interfering, and if x1 and x2 are the distances of the mirrors M1 and M2 from G1, then to the eyes they appear to come from two parallel mirrors separated by a distance x1 difference x2, right? Now what is the pattern of the interference we obtain using Michelson interferometer? Now if we have a camera focus for infinity, then one of the focal plane will obtain circular fringes, each circle corresponding to definite value of theta. Now here is the computer generated interference pattern produced by a Michelson interferometer. These are the 4 different figures for which D is different. D is approximately x1 minus x2. The first figure, which is A, is for a distance of 0.3 millimeter, and B is for 0.15 millimeter. Point D at C is for D equal to 0.14985 millimeter, and for D is equal to 0. And this will be explained later. Now since the beam reflected from the mirror M2 will undergo an abrupt phase change of pi when reflected by the beam splitter, and since the extra path that one of the beams will traverse will be 2 times x1 difference x2, the condition for destructive interference will be 2d cos theta is equal to m lambda for destructive interference, where m is equal to 0, 1, 2, 3, etc., which implies that the centered fringe will be a dark one. We know that d is the difference between x1 and x2, and the angle theta represents the angle that the rays make with the axis, which we have shown in the previous slide. Similarly, the condition for the bright ring would be 2d cos theta is equal to m plus half lambda. So these are the two conditions for destructive and constructive interferences. Now consider an example for lambda is equal to 6 into 10 raised to minus 5 centimeter and small d is equal to 0.3 millimeter. The angles at which the dark rings will occur will be theta is equal to cos inverse m by 1000. So these values will be 0 degree, 2.56 degree, 3.62 degree, etc., corresponding to the values of m is equal to 1000, 999, 998, 997, etc. So what is the inference from this value is that the central dark ring in the figure A correspond to m is equal to 1000. And the first dark ring correspond to m is equal to 999, etc. Okay, now if we reduce the separation between the two mirrors from d is equal to 0.3 millimeter to 0.15 millimeter, the angles at which the dark rings will occur will be theta is equal to cos inverse m by 500, which will be equal to 0 degree, 3.62 degree, 5.13 degree, 6.28 degree, etc. Where the angles now correspond to m is equal to 500, 499, 498, etc. which you can see in the figure B. So what is the difference between the two figures A and B is that when we start reducing the value of D, the fringes will appear to collapse at the center and the fringes become less closely spaced, right? So we have told that when we start reducing the values of D, the fringes will appear to collapse at the center and the fringes become less closely spaced. Now if we change D very slightly, so that D is equal to 0.14985 millimeter from 0.15, okay. So 2D is equal to 499.5 lambda. The central spot in figure B, for which m is equal to 500, would disappear and the central fringe becomes bright, which you can see in the figure C. Thus, as we start reducing the value of D, the fringes will appear to collapse towards the center, and if D is increased, the fringe pattern will expand. These are the two conditions when we change the value of D. One of the important applications of Michelson interferometer is to determine the wavelength of light. If n fringes collapses to the center as the mirror M1 moves by a distance d0, then we must have two equations for which 2d is equal to m lambda and 2d minus d0 is equal to m minus n lambda, where n is the number of fringes collapsed to the center, and on solving these two equations, we get lambda is equal to 2d0 by n. So by this equation we can find out what is the wavelength of the source. Here we need to know only two values, which is d0 and n. d0 is the distance which we moved the mirror M1, and n is the number of fringes which collapse to the center on moving that distance. Now another important application is for standardization of meter. Meter value is standardized by Michelson using the wavelength of one of the light by finding out the wavelength of red cadmium light, okay, which we go through your textbook and refer in detail. Next important use of this device is for the measurement of two closely spaced wavelengths. Now let us assume that we have a sodium lamp which emits predominantly two closely spaced wavelengths, 5890 Armstrong and 5896 Armstrong. The interferometer is first set corresponding to the zero part difference. Near D is equal to 0, both fringe pattern will overlap. So if the mirror M1 is moved away or towards the plate G1 through a distance D, then the maxima corresponding to the wavelength lambda 1 will not in general occur at the same angle as lambda 2. Indeed, if the distance D is such that 2d by lambda 1 minus 2d by lambda 2 is equal to half, and if 2d cos theta dash is equal to m lambda 1, then 2d cos theta dash is equal to m plus half lambda 2. Thus, the maxima of lambda 1 will fall on the minima of lambda 2, and conversely the fringe system will disappear. So it can be easily seen that if 2d by lambda 1 minus 2d by lambda 2 is equal to 1, then the interference pattern will reappear. So in general, if 2d by lambda 1 minus 2d by lambda 2 is half, 3 by 2, 5 by 2, etc., we will have disappearance of the fringe pattern, and if it is equal to 1, 2, 3, etc., then the interference pattern will appear. Okay. Here we conclude the topic of Michelson interferometer. Thank you.